These are filthy. You know, a huge layer of glitter.
Oh, dang.
This one, this one go to.
How's it going, Dr. Tran?
Hey, Chris. Good. How are you?
I'm all right. Just working on the FEA assignment.
It's a hefty one, that's for sure.
Yeah. Yeah. Been putting all my energy on senior design and finally caught a little bit of a break, but figure that I gotta get working on this.
Mhm. Yep, it's that time. Senior design, I think will dominate your life until summer. That's for sure.
Yeah, I'm feeling it already. How's your day so far?
Oh, it's good. Yeah, it's end of the week, so it's tiring, but
Yeah.
you know. Hey, Josh, looks like you're in. So did you want to discuss the economic stuff now?
Hey, Dr. Chen. Sorry for kind of being late.
Oh, no problem. What's up?
I just got home from work not so long ago, but actually I was able to figure it out. I had Brandon help me out a little bit.
Okay, great.
Yeah,
Great.
appreciate it though.
Okay, yeah. If you have any more questions, just let me know. Yeah, we can talk anytime.
Yeah, for sure. Thank you.
Mhm.
Are these going to be on the same notes for the stiffness method?
Yes, so we're gonna finish that. We did get a little bit farther in that in those notes than I thought, and so I'll probably gonna start the next selection note. So it's not in the week 8 link, but if you look in the files, there's the next set of lecture notes there, lecture notes 10 on truss equations, and so I think we'll probably start that one and get a good head start because that one is pretty long. And so I want to make sure we finish all the truss stuff by the end of next week. And so I think it would help to start it a little bit today. Yeah.
All right, cool. Thank you.
Mm-hmm.
Hey, Professor.
Yep. Hey.
If you had a robotic gripper with joints and internal gears and like all these components,
yep.
How would you do Ansys FEA on that?
It's I mean you can try just even loading in the whole CAD file into Ansys and then try that. I think probably the difficulty you might face is that if there's a lot of components, like a lot of like little nuts and bolts and little things like that, it might be difficult to mesh. And so I would probably the way I would do is I would just start with just the entire assembly, load that into Ansys, and then if I see I'm getting trouble meshing, then I would try to suppress. Starting from kind of the smallest parts first, I would suppress the smallest parts, and then keep trying to mesh. And then once I'm able to get a successful mesh, then I would try to run the simulation on that. But yeah, Ansys can handle assemblies. I think it's more of a question of how big your components are and how easily they can mesh.
Would you go in and individually mesh each part, or would you just like let it auto mesh the whole thing?
I would start by letting it auto mesh, and so just seeing what the auto mesher can come up with. It does a decent job, and so just from a perspective of getting a mesh to begin with, I think it does a decent job, and then you can refine it from there. Yeah.
Okay, thank you.
Yep.
Oh, Professor.
Yep.
Would it be safe to assume everything's gonna or lectures are gonna be online until you send us an email?
So we should be. I should be back next week. And so
okay.
Yeah, my fiance did test negative twice, and so I think she's clear. I think she probably just has some other infection, but I feel okay. But my plan right now is to come back by next week. Yeah. I'll send an email just to confirm that tomorrow. All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
Good, how about you?
Busy.
Good, busy, yeah, that sounds about right for this time of the semester. So yeah, hopefully everyone's taking care of themselves. So I know probably a lot of you guys are seniors, so I know senior design is probably ramping up quite a bit for you guys. So you know, I was telling Chris before the lecture that this is usually the time when senior design starts to dominate your life. So you know, best of luck with that, and you know, but just always remember, you know, your health and your mental well-being is always comes first. So always make sure you're taking care of yourself. Okay, and so the plan for today is we're going to finish up our lecture notes on the direct stiffness method. Okay, and so we don't have too much more in that one to go, and so we just have to learn how to apply boundary conditions and do an example. Okay, and so I think that's not going to take too long, and so after that we're going to start our next set of lecture notes, which is on trusses. Okay. And what you'll see from trusses is that it's just another application of the direct stiffness method. It's just that the element stiffness matrix will look a little bit different. Okay, but actually before that, I did want to do a quick Ansys demo for you guys, and so it's not an activity, but you know, over the last week, I know a lot of people have been getting started on their projects, and probably the question I've been getting the most is on how to come up with different loading scenarios. And so I have a quick demo for you to kind of help you know, come up with some other stuff. Okay, or it's to help you better model certain situations that you might have in mind. And so it's actually going to be a demo of one of the appendix lecture notes that I have online, and so it's going to be a demo of A6. But I think for here it's a really good application for that, because you know, basically what we're going to do is we're going to go over how to do you know, that little strip of tape thing on activity 3. Okay, and so if you want to apply a force or some kind of boundary condition on a region in your model that that's either smaller or bigger than an entire face, then this is how you would do it. Okay, and so I'll give a demo on the turbine blade geometry that we have, and I would kind of explain to you, you know, what kind of situation that you would use this for. Okay. All right, and so remember, activity 4 is due next Wednesday, and so make sure you're still working on that. And if you have any questions on that, let me know. Okay. All right, and so I think that's it for the announcements. Are there any questions I can answer about anything before we really get started for today? Is the lab open? I did ask them to open up the lab again today. So is anyone in the lab today? Great, awesome. Okay, yeah, I think it's a little bit hard. So the admin told me he opened it on Tuesday too, but I think someone came in there and then they closed the door afterwards. But he does say that he opens it up every day for students. But I'm glad it stayed open today. Okay, all right. So let's go ahead and do the quick demo. And so you don't have to follow along at all. And so, you know, this is kind of just for your information. And so if you want to do this for your project, you can just, you know, check the recording later, or you can follow the PDF tutorial online too. Okay, and so the tutorial that I'm going to do today is basically how to create a surface for boundary condition application in Ansys. Okay, and so basically the situation is like this. Okay, and so if you have a you know, if you have a certain type of geometry, and so, you know, I think this is probably most common for circular types, and let's say that you want to apply a boundary condition on just this region of the surface, right? Because normally Ansys will model this entire cylindrical surface as one. And so if you try to click anywhere on this surface, it's going to select the entire thing. But a lot of times you don't want to apply a boundary condition on that whole surface. Sometimes you just want to apply a boundary condition on just a small region, okay? And by default, Ansys doesn't let you do this, or at least not easily. And so what I'm going to go over today is how you would actually apply this in practice, okay? And if you're looking for these lecture notes online, if you go to the file section of our website and you go to lecture notes, okay, you'll see that this is appendix notes A6. Okay, and so it's not something that you know, probably outside of today we're probably not going to cover again in the class, but you know, the PDF is there for you, and I kind of walk you through step by step. Okay, but I did want to demo it in the class just so that you know, just to kind of let you guys know that it's probably a good idea to use this or you could use this for your project, okay? In the case where if you were having trouble coming up with different loading scenarios. Okay, and so I've opened up Ansys here, and so I've created a static structural, and I've loaded my geometry, okay? And I've opened up my geometry in Design Modeler, okay? And so that's what I have right here, right? And so here is the turbine blade, okay? And so I'm not sure, probably some people are doing this one, but I haven't gotten questions specifically on this. But I think this is actually a really good model for you to apply the that surface, because it's you have a very large curved surface right here, and maybe you don't want to apply a boundary condition on this entire thing, right? So maybe you want to simulate a case where maybe like some rock or some object is hitting the turbine blade, but it's only hitting it in a small region, okay? And right now you can't do that, because when you try to click anywhere on this surface, it just selects the entire thing. Right? But maybe let's say we want to just apply a boundary condition on just this small region. All right, and so the way we're going to do this is we have to start with a sketch. Okay, so actually let me do this. Okay. And so with the surface selected right here, you can go ahead and click on sketching. Okay. And so what this is going to do is this is going to create a new sketching plane, which is within the plane of the surface, right? And then what you're going to do from here is you're going to draw a region on where you want to apply your boundary condition. Okay? And so let's say that I want to apply a boundary condition in a small circular region on the bottom right side of the fin here. Okay? And so I'm going to go ahead and draw a circle. Okay? And so let's say that the circle, will be just like that big. Okay. And then let's put some dimensions on this just so we can see. Okay, so diameter, let this be 0.0015. I'm just doing arbitrary stuff right now. Okay. All right. And so what I want to do is now that I've drawn this circular sketch here, what I want to do is I want to project this sketch onto the turbine blade right here. Okay. And then what that's going to do is it's going to create a new selectable surface for me to be able to apply boundary conditions. Okay. All right. And so now that we've drawn the sketch, that's all we have to do in the sketch. And so you just have to define your region from there. Okay. All right. And so from here, you have to do a few different steps. And this next one is a little bit non-intuitive. But basically, in order for Ansys to actually recognize this as a valid as a valid sketch of the geometry, you actually have to create a solid model from it. And so you actually have to create some solid. Okay. But we don't want to create an actual solid here. We just want to create like a fake surface or fake solid, so that just so that we can project this onto our geometry. Okay. And so what you're going to do is seeing here that we've created this new sketch here, sketch 1, is that we're going to perform an extrude. Okay. And so for the extrude, we're going to extrude this sketch right here. Okay. And so we're going to extrude the sketch in a certain direction. And actually, let me lower this. Okay. Make it a little bit bigger just so you can see. Right. And so you can see it's a little bit hard to see, but you can see from this circle right here, I'm basically extruding a cylinder that looks like this. Okay. Right. And so that's a cylinder that we want to extrude. But instead of making new material, right? Okay, and so you can see from the bottom right here, we have an option for what kind of operation that we want. Okay, and so the default operation for extrusion is to add new material, but we don't want that in this case. So we just want to create like a fake surface, and so instead we're going to do what's called add frozen. Okay, and so what that's going to do is going to add a new frozen surface, which is something that we're not going to actually use in our geometry. Okay, all right. And so once you went ahead and specified add frozen, you can go ahead and click generate. Okay, and so you can see here that we've created this this new appendage right here. Okay, right. And so now that this cylinder is an actual solid here, we can now take the sketch that we created and project it onto the turbine blade. Okay, all right. And so in order to do that, we're going to go to create, or sorry, we're going to go to tools, and then we're going to go to projection right here. Okay. And then so what projection is going to do is that it's going to let us take an edge, okay, an edge of a surface that we just created, and then project that onto another surface, right? And so the first thing we're going to do is we're going to select our edge. And so let's go to our cylinder down here and select the edge of that cylinder. Okay. Right, and then we have to select the target surface, and the target surface is what we're going to be projecting on. And so I'm going to go ahead and click on target right here, and I'm going to click on this entire surface. I'm going to hit apply, right? And once you've selected the edge and the target surface, we can go ahead and click generate. Okay, and then now you can see here. So before if you saw from before, when we clicked on this turbine surface, we would it would make the entire thing green because that's the that's the surface of the turbine. But now that we've projected this little circle, now this little circle right here is selectable for us to apply a different boundary condition here. Okay, and so if we want to apply a boundary condition, let's say that we have an object that's striking this turbine blade here, then we can do that. Okay. All right, and so the last thing you have to do is we have this cylinder that we created just for this just for this projection, but we don't need it. And so let's go ahead and suppress that, right? And so if you open up this this tree right here which shows all the different parts and bodies in your geometry, okay, you'll see that the second body here, which is the one that we just created, okay, all we have to do is just right click this and then just suppress it. Okay. Right, and now we're back to our original geometry without any appendage, okay? And then now we can select this little region right here for us to apply boundary conditions. And so if I close Design Modeler and open this up in Ansys, then this is going to let me select this little area right here to apply a different set of boundary conditions, okay? All right, and so I just wanted to demo that really quickly, so in case in case you find it useful for your project, and so and so you can use this technique to create, different surfaces and maybe be a little bit more creative in the types of loading scenarios that you come up with.
What was the benefit in doing the frozen?
Yeah, so in order to do the frozen, so right now, just this sketch by itself, it's actually not part of it's actually not a valid surface. Or it's just a sketch. And so basically Ansys allows you to make a sketch just for, maybe just for, like labeling purposes, but it's not actually part of the model yet. And so if you go back to our projection method right here, you can see here that part of the projection was that we had to select an edge. And so that edge actually has to be part of an actual solid surface. And so we can't actually just select the sketch by itself and have that be an edge. And so the reason we made a frozen was to basically take the sketch, we extruded it a little bit, and then from that we were able to create a valid edge. And then with that, we were able to project that edge onto the surface. Yeah. Yeah, it's a little bit of a it's definitely not intuitive. So you have to, you would think that that you would be able to project the sketch by itself. But I think the reason they have that is just so that you can create sketches and not have that affect your geometry at all. All right, any other questions on this?
Yeah, I have quick two questions.
Sure.
I kind of got here a little bit late. So the plane that you made, it doesn't matter if it's exactly on the geometry. It could be like offset off of the geometry and it would still work.
Yeah, you can have it off the geometry. So actually for this one, you can kind of see that the plane I picked is a little bit off. And so I think the most convenient thing is that if you want to project something onto a surface is just to click on that surface, or I'll do a new one just so you can see. And so let's say I want to project something onto this surface. And so if you select that surface and you just click on the sketching button here on the left, then Ansys is automatically going to create a sketching plane that's within the plane of that surface. But if you select like a curved surface, so let's say that we select this bottom one right here, and then you click on sketching, then the sketching plane that it selects, I think, is going to be somewhere. It's going to be somewhere coincident onto that surface. But you can create the sketch anywhere on here, and then you can project it onto the surface. Yeah. So if it's off, it's off. If it's off by a little bit, then that's totally fine.
Okay, thank you. And my other question is, so then once we go back to the model, to the design model, we would have to change the thickness to be really small, right?
Actually, so this method is a little bit different than in activity 3. So activity 3, it's the same idea where we want to create another surface for boundary conditions, but activity 3 actually created like a shell on that surface. This is a little bit different. So this one, we're kind of marking a different region on the surface. And so we're not creating any new bodies here. And so you don't have to specify any thickness for this at all. It's just a marked region of the geometry. Yeah.
Okay, thank you.
Yep. Okay. All right. So hopefully that's useful for you guys' project. And so if remember, if you want to have a kind of if you want to kind of read a document that goes through this, then lecture notes A6 goes through this. Okay. And so you can find that here on the website. Okay. So let me go ahead and bring back my iPad. We can go ahead and continue our lecture notes from Tuesday. All right. And so on Tuesday, we were, we were discussing this direct stiffness method, right? And so basically the idea with the direct stiffness method was to basically give you guys a sense of, how the finite element method actually works in terms of, the mathematics and in terms of the setup, right? Because so far, all we've been doing is just working in Ansys, which is a beast by itself, right? Anytime you're learning a new software, it's always a challenge. But as part of kind of the finite element class, and with this one being the only option that you have as undergraduates, I think I wouldn't be able to, it would be a crime not to show you a little bit of what's going on underneath the hood. Okay. Particularly with regards to a lot of the terminology that's used. Okay. And so last time we talked about, the element stiffness matrix and things like assembly and linear systems, right? And so all of these are kind of terms that are very ingrained in the finite element community. And so, if you left this class without really understanding what those are, and someone tries to talk to you about it in industry, then I would be doing you guys a disservice if I didn't talk about that stuff. All right. And so we are kind of in the middle of kind of going through this entire process. But before we kind of pick up where we resumed, let me kind of summarize that whole process for you here. Okay. All right. And so the first thing you're going to do when you come across these direct stiffness problems is to form the element stiffness matrix for all the elements in your geometry. Okay. Okay. And so so far we've only gone over a single element type, and that's a spring. Okay. But that's enough to get us started. Okay? And so over the next couple of weeks, we'll be going over how to come up with a truss element stiffness matrix, and even a simplified beam. Okay. And so that's kind of where we're going. And so, the only thing that's really going to be different over the next few weeks is step 1 right here. And so, trying to determine what the element stiffness matrices are. Step 2 and 3 are going to be the same for, for all of the direct stiffness problems that we have. Okay. All right. And so step 2 is to assemble. Okay. So step 2 is assembly. Right. And so remember, what assembly means is to basically form the global linear system, right? And so because all the element stiffness matrices are kind of little baby linear systems. And so in order to solve for everything at once, we need to combine everything into one kind of big linear system of equations. Okay. All right. And so step 3 is kind of where we left off. And so step 3 is to apply boundary conditions. Okay. And so kind of the net effect of the boundary conditions, or what they're going to do, is they're going to modify our global linear system. And the goal with the boundary conditions is to make it actually solvable. Right? Because if you remember from Tuesday, you know, after we assembled all of our element stiffness matrices, we ended up with a symmetric global linear system, which is something that we can't solve right now because you can't find the inverse of a symmetric matrix. Okay. All right, and so once step 3 is done, that's all the hard part, and so step 4 is just to simply solve. Right, and because you know these linear systems can get pretty big most of the time, this solve step right here most of the times is going to be performed with some kind of numerical tool. And so the one I use is Matlab, just because that's what I'm familiar with. But apparently you can also solve linear systems in like Excel too, or even, you know, I know there's probably a bunch of websites out there where you can just punch in the numbers and solve it. So. And so for this class, you know, you'll see that when we're doing problems and when I assign them to you for homework, you know, you're going to end up with big linear systems. And so I do not want you guys solving those by hand. I mean, you're welcome to, of course. And so if you're really into that stuff, I'm not going to stop you. I think I personally, I'm into weirder stuff than solving linear systems by hand, but you know, that's why I'm not going to judge you. But I think for most people, it's going to be more time than it's worth. And what I really want you to focus on is kind of steps 1 through 3 here, and then not get bogged down with the algebra in step 4. And so once you get to step 4, if you want to, if you have, you know, whatever computational tool is your favorite for solving linear systems, then by all means, please use that. And so don't feel like you have to solve these by hand. Yeah. Okay. Yeah, I know not everyone's a fan of Matlab, and that's understandable. You know, I can understand that. And so you know, feel free to use whatever you want. So I'll show you how to do it in Matlab. And it's not that bad. I mean, of course, you know, I have a different perspective than probably other people, but basically all you're solving is just a system of equations. And so whatever method that you find the easiest for that, then go for that. Yeah. SolidWorks and CATIA. Oh, can you solve linear systems in SolidWorks and CATIA? That would be that'd be really cool if you could. Okay. All right, and so this is kind of the general process that I want you guys to go through, and basically all of the theoretical FEA is going to be following this exact process. So this is one that you're going to be very familiar with. Okay, and even though we're doing this for a direct stiffness method, you know, this process right here is basically the same for all finite element methodologies, right? And so inside Ansys, I guarantee you that they're following these 4 steps as well. Okay. The biggest difference that you're going to see between the direct stiffness method and the Lurkin method is another popular method, or you know whatever Ansys is doing under the hood. The biggest difference between all the different methods is in step 1. Okay, and so that's where all the variance happens between the different finite element implementations. But the assembly, the applicate, maybe you'll see a little bit of difference in step 3, but not nearly as much variance as step 1. But assembly, applying boundary conditions, and solving, you know, all of that is the same. Okay, and so you know, I want to make sure that you know, you guys are familiar with this process at least in theory, just so that you kind of know, you kind of understand a little bit what's going on underneath the hood in Ansys. Okay, any questions on this? Okay, all right, so let's go ahead and pick up the kind of the walkthrough, not really an example, but the walkthrough of what we were doing before, okay? And then let's talk about how we can apply boundary conditions, okay? All right, so the situation we were looking at was we had 2 springs, okay? And they were connected to each other in series, okay? And we're pulling on the springs with a force F1, okay? Or sorry, just a force F, sorry. And our 2 springs have their spring constants K1 and K2, okay? And so this is, oh, sorry, this is Ka, Kb. I'm using numbers for the nodes and letters for the elements, okay? All right, and the nodes, we have node 1 that's attached to the wall, node 2 that's attached, you know, between the 2 springs, and node 3, which is on the outside, okay? And so last time we formed the element stiffness matrices, and we assembled them into the global system. And then we got a global linear system that looked like this. right? And so we had 3 nodes, and so we have a 3 by 3 system. Okay, and so we have F1, F2, F3 is equal to KA minus KA minus KA, KA plus KB minus KB minus KB, KB. Okay, 0, 0. And this is D1, D2, and D3. Okay. All right. And remember, the way that we got this was that we basically placed the element stiffness matrices in their respective location, right? And so element A took up these slots right here because they were modifying nodes 1 and 2, whereas element B was occupying these slots right here. Okay. Because they were occupying, because they were modifying nodes 2 and 3. Okay. All right. And so the next step in order to actually make this solvable is to apply boundary conditions. Okay? And just like I mentioned on the previous page, basically the effect the boundary conditions are going to have is they're going to modify this linear system, in order to make it solvable. Okay. All right. And so remember, we have 2 types of boundary conditions, right? And those 2 types of boundary conditions are going to have different effects on how they modify our linear system. Okay. All right. And so let's start with constraints. Okay. And so remember, constraints are things like fixed supports, things like displacements, right? And what they do is basically they basically directly specify our solution variable. Right? And so if you look at our geometry here at the top, right? And if you look at nodes 1, 2, and 3, you can see that node 1 here is subject to a constraint, right? And in fact, it's fixed to the wall. Okay. Okay. And so if you think back to our Ansys activities, when we have a fixed support, what that basically means is that the displacement or the deformation at that location is going to be 0. Okay. And so what this tells us is that D1 is going to be 0. Right. That's the boundary. That's the fixed support boundary condition that we have on node 1. Okay. And so the goal now is to see, how can we take this equation right here where D1 is equal to 0, and how can we actually implement that into the global linear system? Okay, and so we'll do that on the next page. Okay, any questions on this? Okay, all right. And so to kind of motivate what we're going to do, let's kind of just remind ourselves that this global linear system right here, it represents a system of 3 equations and 3 unknowns, right? And so in order to see that, we can perform this matrix multiplication. And so if we take this row of the matrix here and then multiply by this column vector, that's going to give us our first equation, right? Right, and so just basically just reading off the first row in the matrix there, what we have is basically F1 is equal to KA times D1, okay, minus KB or minus KA times D2 plus 0 times D3. Okay. And so if we multiply across the first row in the matrix, that's exactly what we get, right? And so we get this equation. All right. Good. Let's compare that to our boundary condition here, okay? And so our boundary condition basically says that D1 is equal to 0, right? And so another way we can say that 0 is equal to D1, okay? Right. Let me augment this equation right here to also include D2 and D3, right? And so if I augment this equation to say that this is also equal to 0 times D2 plus 0 times D3, okay? Okay. And so you can, hopefully you can see that, when we multiply 0 by D2 and D3, it gives us basically the exact same thing, right? Because 0 times D2, that's going to cancel out. 0 times D3, that's going to cancel out, okay? And we still get D1 is equal to 0. Right? And so why would I do this? So why would I go through the trouble of adding these terms if they just cancel out anyway, right? The reason I did this is so that I can basically match the same form as this equation up here, right? And so you can see, if we compare this to the equation that we got from the matrix, we have a D1 term, we have a D2 term, and we have a D3 term, okay? Right? And so basically what we can do is we can say that, instead of having this equation, okay, and so instead of having that equation, why don't we just replace this with an equation that represents our constraint boundary condition? And so what would that row in the matrix look like, right? Because right now we have F1 is equal to KA minus KA 0 times D1, D2, D3, okay? What if we instead replace this with 0 is equal to 1, 0, 0 times, oops. Wait, go back. What the heck? Okay, that was weird. Okay, what if we instead replace this with 1, 0, 0, D1, D2, D3, okay? Right. And so this is an equation that will satisfy our boundary condition, okay? Much more than this one, right? And so let's go ahead and cross this one out. Okay. And then now let's go ahead and rewrite our linear system, our global linear system that has this new equation instead of the old one, okay? Okay. All right, and so before we had a F1 up there, but instead we're gonna have a 0 now, okay? And so we're gonna have 0, and the first row is now gonna be 1, 0, 0, okay? But the rest of the matrix is gonna stay the same. So we're gonna have minus KA, KA plus KB, minus KB, 0, minus KB, and then KB, okay? We have D1, D2, D3, okay? Right? Okay. And so this is now our new linear system with the constraint boundary condition applied. Okay. And so just to kind of summarize what we did. Okay. And so whenever you have a constraint type boundary condition on a node, you're going to replace an entire row in the matrix with that boundary condition. Okay. All right. And so that's how we're going to do that. Okay. All right. Any questions on constraint boundary conditions? Okay.
Yeah, good question. Is this kind of saying that the applied force is 0, or and there still might be reaction forces, or all of that is 0?
Yeah, and so we're there could definitely still be reaction forces, and actually there will be, because there's a
Right.
fixed support. But all we're saying right now is just the displacement is going to be 0, because when you're first solving the system, the thing you're solving for first is actually this guy. Okay. And so remember, displacement or deformations, those are our primary variables. And so you know, the first thing when we first solve this linear system, that's going to be the first thing that we solve for. And then once we have that solved, then we can compute like reaction forces from there.
Okay, thank you.
Yep. Okay. And so those are constraint boundary conditions. And so that's actually the more complicated one. Okay. And so when you're doing these finite element problems, I would say do your constraint type boundary conditions first, because that changes the matrix quite a bit. Okay. And next we have our loads types. Okay. So loads are really easy. Okay, because loads are not going to touch the matrix at all. Okay, and so the only place where loads are going to modify are in the forcing vector. Okay, and so the forcing vector is this guy right here. Okay, and so it's the vector kind of off on its own on one side. Okay, and so when you have load type boundary conditions, you basically just plop them right into the forcing vector. Okay. And basically we're going to go load a node by node here, and then see, you know, what loads are being applied there. Okay. And so if you have a node where no load is being applied, then you just put 0 there. Okay. Okay. All right, and so let's go node by node here, and then let's see, you know, which loads are being applied. Okay, so let's start with node 2. So node 2 here, we're not really doing anything to this node, and so the load F2 is going to be 0. Okay, and then for node 3, you can see that we have a positive force F. Okay, and so then our boundary condition there is going to be just positive F. Okay. All right, so let's go ahead and put those in. Okay, and so for node 2, we have no load, and so we put a 0 there. But for node 3, that's where our external load's being applied, and so we're going to apply a force of F right there. Okay. All right, and so with those things settled, you know, we settle upon our final global linear system. Okay. And this one is ready to solve. Okay. And so presumably, you know, you'll be given the values for the spring constants. And of course, you'll be giving the values for the loads. And so this is a matrix that you can just pop it into Matlab or pop it into whatever, you know, your favorite way to solve linear systems. And you can be able to solve for D1, D2, and D3. Okay. All right, and so next I'm going to do an example that kind of takes this process from front to back, and then it has numbers in it too, so we can kind of see the entire process. And then we'll, and then you can kind of see it all in action. All right, so before I do that example, are there any questions on this? Okay, all right, so let's go ahead and do that example. So I think, with the symbols and kind of the fact that we went really slowly, I think it's hard to get a good sense of how everything kind of fits together. So hopefully with this example, it'll be a bit more clear. All right. All right, so let's say that we have a spring system that looks like the following. Okay, so let's say that we have a wall right here. Okay. We have one spring that's attached to the wall. Okay. And so now let's say that this spring here is attached to a wooden block. Okay. And then this wooden block itself is attached to two springs. Okay. So let's say that we have one spring up top right here. Okay. Another spring right here. Okay. Okay. And so let's go ahead and label all of these elements here. Okay. And so this first spring on the left here, this will be element A. This spring right here up top will be element B. And this spring on the bottom right here will be element C. Okay. Element A has a spring constant Ka. Element B has a spring constant Kb. And element C has its spring constant Kc. And I'll give values for that in a little bit. Okay. And then the nodes, we have to label the nodes too. Okay. And so node 1 is going to be attached to the wall on the left. Okay. This entire wooden block, because all these attachments here they're on the same block, and so this entire block is all going to move together, and so we'll call this entire block node 2. Okay. This top node on the right here we'll call node 3, and this node on the bottom here we'll call node 4. Okay. And we have two loads being applied, and so on node 3 we have a force to the right. We'll call that F3. And node 4, we have a force to the left. We'll call that F4. Okay. All right. And so let me go ahead and give values for all of these parameters. Okay. So let's say that Ka is equal to 500 newtons per meter. Okay. Kb, this one is 100 newtons per meter. Okay. And Kc, this is 250 newtons per meter. Okay. And the loads, we'll say that F3 is equal to 100 newtons. And F4 is equal to 50 newtons. Okay. Right. And the goal of this analysis here is we're going to use the direct stiffness method to solve for the displacements of all four nodes. Okay. All right. And so this is a fresh, brand new finite element problem. And so we're going to take it from the top and then kind of walk through this entire process. Okay. All right. Any questions on just the setup for the problem? Okay. All right. So let's go ahead and run through the entire process. Okay. And so remember, the first thing that you have to do when you come across a problem like this is we're going to write out all the element stiffness matrices for the elements. Okay. Okay. And so here we have three elements. And so we have element A, element B, and element C. Okay. And so we're going to have three element stiffness matrices, and they're all springs, right? And so remember, for a spring, our element stiffness matrix system looks like the following. Okay. Okay. And so remember, for a spring, we have a 2x2 element stiffness matrix. And so you just simply put the spring constants into this matrix like this. Okay. Okay. And then you specify which nodes that they're working on. Okay. And so on the next page, I'm going to go ahead and fill those in. And I'm going to go ahead and plug straight in with the values of the spring constants for each of the springs. Okay. And so you'll see kind of how that's done. Okay. All right. Any questions on this so far before I turn the page? Okay. All right. So let's go ahead and write out the element stiffness matrices for each of the elements. So let's start with element A. And so for element A, remember we have Ka is equal to 500 newtons per meter. Okay. Okay. And so the element stiffness system for element A is going to be F1, F2. Okay. Remember, because element A here is touching nodes 1 and nodes 2, right? And so those are the two node numbers that we're going to use. Okay. We're going to go ahead and put in the stiffness, the spring stiffness now. Okay. So you have 500 minus 500 minus 500, 500. Okay. And this can be multiplied by D1, D2. Okay. All right, element B. So element B here has a KB of what? 100 newtons per meter. Okay. And the nodes that element B works on are nodes 2 and 3. All right. And so the element stiffness matrix for element B is going to be F2, F3, okay, is equal to 100 minus 100 minus 100, 100, okay, and then D2, D3. Okay. All right, and so finally, let's do element C. All right, so element C, the Kc for that one, or the spring constant for that one, is 250 newtons per meter. Okay, and the nodes that it works on are nodes 2 and 4. Okay. So this one's going to be interesting to assemble because it's not all going to be in one contiguous block. Okay. All right. So for element C, we have F2, F4 is equal to 250 minus 250 minus 250 and 250. D2, D4. Okay, and so we've written out all the element stiffness matrices, and so the next step that we're going to do is assembly. Okay. All right. Any questions on this?
Yeah, it wouldn't matter, right, if we have our lowercase f as capital F.
Oh yeah, no, that doesn't matter, and so you can call whatever you want.
Okay, thank you.
Mm-hmm. All right. Okay. So let's go ahead and let's put together our global linear system and see how all of these fit together. All right. And so the next step, now that we have all the element stiffness matrices, is assembly. Okay. Okay. And so here we're going to have a 4x4 system because we have 4 nodes. Okay. So we have F1. F2, F3, F4, okay. Okay, and then we have D1, D2, D3, D4. Right. And so just to kind of help us out with the organization, I'm going to go ahead and label the columns as well. Okay. All right. And so let's go ahead and start assembling the element stiffness matrices here. Okay. And so I'm going to use colors just because I can, just to make it a little bit easier to see. Okay, so let's start with element A. And so element A, we know works on nodes 1 and 2. Okay, and so it's going to be on the D1, D2 block of our global linear system. Okay, and so we're going to go to all the columns that have D1 and D2 and all the rows that have D1, D2. Okay, and you can see that they all intersect in this region right here. Okay, and so that's going to be element A. Okay, and so element A is going to cover that that region right there, because that's everything that has to do with nodes 1 and 2 combined. Okay. All right, I'm not going to fill in the values just yet because I want to kind of focus on just locating these elements first. Okay. Element B works on nodes 2 and 3. Okay, and so we're going to go to all the rows and all the columns that have to do with 2 and 3. Okay, and so that's going to cover this region right here. Okay. All right, and so you can see that we have overlap on node 2, right? The D2 spot. And that makes sense because both elements A and elements B are going to be, interacting on that spot. They both border that node. Okay. All right, and so finally, let's do element C. Okay? And so this is the interesting one. Okay. And so element C, from the previous page, we know that it borders nodes 2 and 4, right? And so 2 and 4 are actually not connected in this linear system at all. Okay, I think the tempting thing to do when you're first starting out is to make a box around this region right here. Okay, because that's just kind of what we've been doing. But element C here doesn't touch node 3 at all, right? And so if you go back to our original diagram here, right? Node 3 is up here, whereas element C is down here. Right? And so element C doesn't touch node 3 at all, but it does touch node 2. And so when we do insert the components of the element C element stiffness matrix, you need to make sure you do it on only the nodes that are, have to do with nodes 2 and nodes 4. Okay. And so it's not going to be all connected. And so that's okay. Right. And so let's start by looking at all of the regions that are crossed by 2 and 4. Right. Right, and so the first one we're going to do is D2, D2, okay? And so we have the D2 column right here and the D2 row right here, okay? And you can see that they intersect on this D2, D2 spot right here, okay? And so we're going to have another green border around here, okay? And so this spot right here is very popular, okay? So all 3 element stiffness matrices are going to be modifying it. Next, we have the D2, D4 slot. And so we have D2 row D2, column D4. And you can see that they intersect on this spot right here. Okay. And so we're going to draw another box right here. Okay. Same thing for the D4 row and the D2 column. Okay. So that's going to be right down here. And then finally, we have the D4, D4 spot, which is right here. All right. And so those are all the locations where you're going to insert the element stiffness matrix for, for element C. Okay. Okay. So is that any questions on that, on why we chose these locations for these elements? And of course, just like we did last time, any place that's not boxed, we can just go ahead and fill in a 0 for those locations. Okay, and so now that we have the locations picked out, let's go ahead and insert the values. And so let's go ahead and do element A first. So element A's spring constant is 500. And so we do 500 minus 500 minus 500, 500. Okay. Next, we have element B, which is 100. And so we're going to have a plus 100 because we have an intersecting here. Okay. Minus 100, minus 100, 100. Okay. And finally, element C. Element C, we have 250. So we're going to add 250 on this spot right here. It's getting a little bit crowded. Okay. Minus 250, minus 250, and 250. Okay. All right. And so the only place where we actually have any overlap is on D2, D2. So let's go ahead and perform this arithmetic. And so we have 500 plus 100 plus 250. And so that gives us 850 overall. Okay. All right. And so now we have our linear system here. And then we're now ready to apply boundary conditions. Okay. All right. Any questions on how we got this? Okay. All right. And so last thing that we can do here is we can go ahead and apply the boundary conditions so that we can actually solve this. Okay. All right. And so we have 3 boundary conditions here. And so we have one constraint here on node 1. Okay. And so remember, when we have a constraint boundary condition, that's going to replace the entire row. Okay. And so we're going to replace this entire row. Okay. And so we're going to replace this entire row with with zeros on all the off diagonal parts, okay, and then a 1 on the main diagonal, okay. And then in the forcing vector, we're going to go ahead and just insert a 0 there. Okay. All right, and then the last thing we're going to do is insert our loads. Okay, and so we know that we have a load of F3 on node 3, right? And so what is the value of F3? F3 is a positive 100. Okay. And remember, for the loads, we can just plop those just straight into the forcing vector. And F4 is going in the negative direction, and so we're going to put a minus 50 on that one. Okay. Right. And then node 2, since we don't have any loads there, we're just going to just put a 0 there. Okay. All right. And so now our global linear system is complete. And so what you can do from here is you can just insert this into Matlab or whatever system or whatever whatever program that you like to solve for linear systems. And so again, please don't solve this by hand unless you're into that stuff. But I did this in Matlab. Okay. And so if you do this in Matlab, we get the following solutions. Okay. And so if we plug this in Matlab, we get D1 is equal to 0. Okay, which makes sense because that's our fixed support. Okay. D2 is equal to 0.1 meters. D3 is equal to 1.1 meters, and D4, because we're kind of compressing that that node in, we actually get a minus 0.1 meters. Okay. All right. And there's our solution. Okay. All right, and so okay, we have about 15 minutes left, and so let me show you the code that of how you can actually input this in Matlab, just so that you have those tools available, and then just whatever time is left, we'll use that to start the truss equation notes. Okay. All right. Any questions on this before we jump into Matlab? Okay. All right. And so to solve linear systems in Matlab, you basically only need to do a few things, okay? And so first thing we're going to do is we're going to basically put this matrix here and encode that in Matlab, okay? And then the other thing we need to do is we need to put in the forcing vector and put that in MATLAB. Okay. And then once those two things are in, then MATLAB can just take us from there. Okay. All right. So let me go ahead and switch back to my laptop screen. Okay. Let's kind of, does everyone have this matrix written down? This matrix here, because we're basically going to be inputting these values kind of directly into MATLAB. Okay. All right.
Quick question, sorry.
Sure.
It just popped in. Regarding the node 2, would it matter the placement of the nodes? Like for instance, in this case, I'm assuming all the nodes are directly like on top of each other. But would it matter if the one connected to node 3 or node 4 are kind of like offset from that axis?
Yeah, so for this case, it doesn't matter too much. So the important thing is that all of those things are going to displace and deform together. And so kind of the key for that is because they're all kind of attached to the same block, and we're going to assume that the block is relatively rigid. And so, if you put the nodes kind of off center right here, it doesn't make too much of a difference. The most important thing is that they all kind of move together when we kind of force the springs. Yeah.
Okay, got it. Thank you.
Yep. All right, so let's go ahead and jump into MATLAB. All right, and I conveniently have it open just because my calculator is out of batteries and I'm too lazy to drive down to the pharmacy to get new ones. Okay, so let me go ahead and clear this. Okay, and so to solve this, system in MATLAB, can everyone see my console? Okay. And so if I type this, can everyone read it?
Yeah.
Yeah.
Okay. Good. And I remember before I had my font a little bit too small. Okay, and so the basically what we're going to do in MATLAB is we're going to make a matrix that has these values exactly. Okay, and we're going to make a vector that has these values exactly. Okay, and then we're just going to tell MATLAB just to solve it for us. All right, and so the you can call, and so the way you use MATLAB, remember, is you define everything in terms of variables, right? And so we need to make a variable that stores our matrix right here, okay? And so the variable name that I usually use for a matrix is I just use A, because essentially, we're solving, we're solving the linear system AX equal to B, right? And so traditionally the name for the matrix in a linear system is A, or you can be a bit more descriptive. You can call it LHS matrix, and so I've done this before. But you can choose whatever you want for the name. All right, and so to denote a matrix, we're going to use square brackets like this, okay? And we're going to build up this matrix row by row, okay? And so from the left, you can see that the first row in the matrix is 1, 0, 0, 0, right? And so each entry in the matrix, you're going to separate with a comma, okay? And then to go to the next row, you're going to use a semicolon, okay? Okay, and so now we're going to input the next row in the matrix. And so the next row in the matrix is -500, comma, 850, comma, -100, comma, -250, okay? And so this is the second row in the matrix right here, okay? So that corresponds to this guy right here. Okay. Next, we're going to input the third row. And so third row is going to be 0, comma, -100, comma, 100, comma, 0. Okay. And then finally, we're going to put in the last row. And so the last row is going to be, let me move my mouse. The last row is going to be 0, comma, -250, comma, 0, comma, 250. Okay. All right, and so once you've input all the entries in the matrix, you can just go ahead and hit enter, okay? And then you can check, and then, once you hit enter, you can see that I've created this new variable called A right here, okay? And so you can go ahead and double click this, and you can just verify just to make sure that the matrix here looks exactly as the one you have here, right? And so you can see here we have 1, 0, 0, 0 for the first row, -500, 850, -100, -250 for the next row. Third row is 0, -100, 100, 0. And the last row is 0, -250, 0, 250. Okay, so we're all good in the hood. Okay, and so the next thing we have to define is the B matrix. Okay, and so that's going to be our forcing vector on the right side. Okay. All right, and so I'm going to use the same notation that I used for the matrix there. Okay, except I'm going to separate every entry with a semicolon. Okay. As remember, this is supposed to be a column vector, right? And so the first entry is going to be 0. And so we're going to do 0 semicolon, 0 semicolon, 100 semicolon, minus 250. Okay. All right. And so that's going to be our right-hand side matrix, our right-hand side vector, sorry. Okay. So go ahead and hit enter. And we can go ahead and check this just to make sure that it's correct. You can kind of see it from there, but there we go. Okay. But just to make sure that it's oriented in the way that we want, we see we have 0, 0, 100 minus 50. So that's good. Okay. All right. So now that we've created variables for both of our our global linear matrix and our global forcing vector. Okay. Now all we have to do is create a variable for the solution. Okay. So we can say that we can make a new variable called solution. Okay. And the special command that you're going to do is basically just this backslash operation. Okay. So you're going to take your matrix, the variable that you use for the matrix, and then you're going to do backslash, and then the variable that you use for the vector. Okay. Have you guys seen the backslash operator before? Has a previous class used that that you've seen before?
First time I've seen it.
Okay, yeah, that's kind of my experience too, which is a shame because I think the backslash is one of the most useful features in Matlab. So eventually, the department keeps promising me that I'll teach 205 someday, but it just never happens. But I know that when I teach 205, I'm going to teach them backslash because it's really useful. Okay, and so all we have to do is just hit enter. Okay, and so this is our solution. Okay, and so basically the backslash is basically MATLAB's way to say solve this linear system. Right. And so you can see here that we get the exact same solution that we got here. And so the first entry in our solution is our D1. Okay, so we see that our first entry is 0. The second entry in solution, that's our D2. Okay, so we see we got 0.1. Our third entry is D3, and we see we got 1.1. And then our fourth entry, which is D4, is minus 0.1. Okay, and that's all there is to it. And so to solve linear systems in MATLAB, the only thing you have to do is just define your matrix, define your vector, use the backslash, and then you're done. Okay. All right. Any questions on this?
So what exactly does the backslash do?
Yeah, good question. So one way that you can think of the backslash is, you have this linear system right here, A is equal to B, right? And so one way that you can think of it is you're basically multiplying both sides of the equation by inverse of A, right? Actually, I have this right here. Right? And so normally you have AX is equal to B, right? If you multiply both sides of this equation by A inverse, right? And so the A inverse is going to cancel out the A's on both sides. Okay? And so you're going to have X is equal to A inverse B. Okay? And so actually you can do that operation in MATLAB too. And so you can say that solution is equal to INV. And so INV is the MATLAB command for doing inverse. And so you can do inverse of A multiplied by B. Okay. And so you can do that and you get the same thing. It's just that this method right here, it'll work, but it's just a tad slower than backslash, and it's a little bit more annoying to write to because you do INV A times B. So the backslash it does the same result as this, but it uses a smarter algorithm for that. Yeah, and so it uses a computational linear solver, which is a lot more efficient than trying to find the inverse of a matrix, because finding inverses of matrices is usually a pretty difficult task. But in essence, this is what it's doing. Yeah. Mm-hmm.
Yeah, I really wish Sanders taught us that.
It's
a lot more convenient.
It's MATLAB is a very diverse software, and I think everyone kind of has different features in MATLAB that stand out the most for them. And so for me, I use MATLAB a lot to solve these linear systems, and so that's why I think this is an important feature. But yeah, Dr. Sanders has his own features that he thinks is more important too. So that's why I want to teach 205, because I want to get my chance to kind of teach that stuff. Yeah. Okay. Any other questions on the MATLAB stuff? Okay, so we have 5 minutes left, and so I think that's just enough time to kind of introduce the idea of trusses before we kind of wrap it up for the week. Okay. All right. So the next topic that we'll pick this up on next Tuesday is truss equations. Okay. All right. And so, up to this point, you've been introduced to the what's actually formally known as the finite element method, right? And so the true finite element method is, finding element stiffness matrices, assembling them into a global linear system, applying boundary conditions, and solving it, okay? What you're doing in Ansys is Ansys basically automates all that for you. And so they put a nice graphical user interface on top. But at its core, that's what finite elements is all about, is taking a physical problem, which is defined by very complicated differential equations, and then turning it into a linear algebra problem, right? And so we saw that whole process kind of unfold before our eyes with springs. Okay. But and that's all great. But springs are not the most realistic thing. I mean, springs do exist. They're real stuff. But if you're talking about what are actual real structures made out of, we don't really use springs all that often. Okay. And so kind of the next step up from springs is to use truss elements or bar elements in order to so that you can form a structure. Okay. Okay. And so if we want to draw a truss element, it's actually not the most exciting thing in the world. Okay. A truss element is basically just a thin cylindrical rod. Okay. Or in this case, a thin cylindrical bar. Okay. And so we can use these to build a lot of structures out of. And so, probably you guys have already learned the statics of, of how trusses work. Okay, so I don't need to explain that to you again. But we can actually use these in finite elements too. Okay, and actually using the exact same method as the springs that we just went over. Okay. Okay. The biggest difference that we'll see for truss elements versus springs is that the element stiffness matrix is going to look different. Okay. That's the only thing that's going to be different. And so, and so you'll see on Tuesday, we're going to start with 1D truss problems. The exact process that we just literally just followed in the last example, we're going to do that for the truss elements too. The only thing is that the element stiffness matrix is going to look different because obviously, a bar or a truss element doesn't have a spring constant. Okay. And so I'll give you a little bit of sneak preview. And so on Tuesday, we'll actually derive this and see how this is. But the element stiffness matrix for a truss bar looks like the following. Okay. And so it's a 2x2 system, just like before. Okay. But instead of the spring constant, we're going to have a combination of the cross-sectional area A, the Young's modulus E, and the length of the bar L. Okay. where A here, A is cross-sectional area. Okay. E is the Young's modulus of the material. Okay. And L is the length. Okay. And so if you know those quantities, then you can form the element stiffness matrix for the truss, and you can just follow the exact same method that we would just went over, for the spring one. Okay. All right. Any final questions on this before we wrap up for the week? Okay. All right. And so that's all we got time for. So thank you guys for tuning in, and thank you guys again for being flexible this week and meeting virtually. The plan right now is for me to be back on campus on Tuesday, and so I'll send an email tomorrow just to remind you. And so I think everything should be good over the weekend. Okay. All right. So thank you guys for tuning in. I hope you guys enjoy your weekend, enjoy the rest of your evening, and I'll see you next week.
Dr. Tran, I have a question about the. Can I ask now?
Sure. Yeah. Mhm.
About the activity